record. Okay, we're recording now. Okay, okay, here I'm gonna give you this code 7. I'll just put it into the chat. Okay, I have in the chat the six character code for Desmos Activity Builder. This is just a way for you as we go through the problems to kind of show that you're following along. Some people have told me they have some trouble, and those people have been direct, sort of private chatting me their solutions. So that's fine also. But it's good for me as a teacher to see, people filling out the different things. Now I want to show you an advanced technique for division. And I'm going to utilize as an example how to do 2 divided by 13. And this is pretty tricky. Oh, I hear an echo of myself. So if you're not muted, maybe you're not muted. Let me see if I can mute everybody.
Yeah, I think somebody's on mute.
There you go. That's okay. I'm going to mute everybody right now. Okay, you're all muted now. So here's this 2 divided by 13. This is going to require a little trick. So far we haven't really needed that many tricks. We had the 1/3, we had the 2/3, we had the taking half and then half and half and half. Sometimes we did 2/3 and worked our way down to 1/3 and to 1/6. And sometimes we needed a random other thing, like a 5th or something like that. And I said we can kind of cheat a little bit, and we are going to be able to cheat a little bit, but just want to show you what to do when it gets more complicated. So when you're doing 2 divided by 13, we say 1/13. And I'm going to try half first, because sometimes half is a bit of a dead end and you end up needing 2/3, but you might as well try half and see where it's getting you. Well, it's still bigger than 2, so we do a 1/4. And it's still bigger than 2, so we do an 1/8. And we end up with 3 becomes 1.5, and 1/4 becomes 1/8. And this is good. It's pretty close to 2, but it's not 2. It's 1 5/8, just in modern terms. So we need 3/8 more.
I'm sorry, this doesn't seem right. It's 2 divided by 13, not 13 divided by 2.
True, but the very first step in doing 2 divided by 13, in creating this chart, are you talking about the 6.5 that's hanging out right there?
No, I'm talking about this whole thing. You're doing 13 divided by 2, not 2 divided by 13, because the answer wouldn't be almost 2. It would be like a decimal. It'd be a fraction.
Right. No, the answer is going to be coming up on the left-hand side. These things on the left-hand side are going to.
Right. I'm sorry.
When the right-hand side gets to 2, the corresponding entries in the left-hand side. So the answer is going to be around 1/8. The answer is 2/13, which is, not that far from 1/8.
Yeah, I agree. I agree with my colleague. I always thought that the number on the left goes on the right-hand side and the number on the right goes on the left-hand side. That's how I was doing it.
Oh, remember,
Well,
I actually clarified that with Professor, that, right? Division, it
With
goes
multiplying,
right.
when you're multiplying, you do it that way. But when you're dividing, you.
Thank you.
Because when you're dividing 2 divided by 13, you're basically saying 13 times what equals 2. So the 13 is actually on the left-hand side. It's on the left-hand side of the corresponding multiplication problem. But if you want to think of it as with division, we use the thing on the right, the thing you're dividing by, as what goes into your chart. Scott had mentioned this because it did seem inconsistent. But with multiplying, we use the thing on the left. We could use the thing on the right for multiplying. We still get the right answer. But for dividing, we must construct our chart. Because we're looking for multiples of 13 that add up to 2. Now, usually this number on the left is bigger than 13. You know, it's like 104 divided by 13. You know, but that's not what this question was. This was a small number. It's smaller than 13. So we're going to expect small fractions down here.
Oh wait,
Now we're
it can't
in,
be just an eighth because that didn't add up to 2.
those don't add up to 2 yet. 1/8 is just is going to be used, but it's not done because we're going to need more. We
Okay.
need the 3/8 more.
Hmm.
We need 3/8 more. So that's going to be a little tricky. So here comes the sneaky trick for how to complete this question. We can take the 3/8, and write it as a sum of powers of 2. So 1 plus 2 over 8, which is 1/8 plus 2/8. And which I could then write as 1/8 plus 1/4. So that's their way of saying 3/8. 1/8 plus 1/4.
Oh, I see.
Now there's going to be a sneaky thing. I'm going to show a weird step here. They wouldn't do this step, but I'm going to show it because it's kind of implied. To get 1/8 and 1/4, I'm going to do this step. I'm going to just do something kind of weird. I'm going to say 1/13. Whoops. I'm going to say 1/13 equals 1. Of course, if I just do 1 over whatever my chart is based on, it's going to be 1. They actually wouldn't write this step, but I'm just going to put it there in parentheses. Then they would jump to 1/8 by multiplying the denominator by 8. So 1 over 13 times 8 is 104. Now they would actually not put the 1/13 one step. So what I'm getting at here is that in the denominator, I put 1 over 13 times whatever. And then here, it would just be 1 over n. So if you multiply the denominator by something, if you multiply 13 by something and put that as the denominator right here, on the right-hand side, you're going to have 1 over the thing that you
Multiply by 2?
multiply by 8. Oh, and now, yes, because remember, it was 1/8 plus 2/8.
Yeah.
So the next step would be to double everything. Sorry, I
Yeah.
ran out of room here. I really should have paced this better, but the next step is sorry, I'm going to, I'm not in a big rush, so I can slow down a bit here and write it a little bit better. Let me see if my pen is charged now. Strange. Okay, so here's where I was. I was at 1/8. That's 1/1/2, 1/8. And then I needed 3/8, which is 1/8 plus 2/8. So I got to the 1/8 by doing 1 over 13 times 8, which is 1 over 104. But I also need the 2/8, so I double both of those and I get 1 over 52, and that becomes 2/8, which is 1/4. And I'm finished with this question now because I've accomplished I got the 3/8 that I needed to put together with the 1/8 that this thing that I already had. That was 1 and 5/8 was already accomplished here. And these two things got me the 3/8 that were needed. So the answer to this question is 1/8, 1/52, and 1/104. And that is the exact thing that we see in the 2/n table.
Can you just go over that one more time, please?
Well, the critical step was, and I'm going to make a new page here.
Okay.
The critical step is, if I somehow like wish that I could get, I wish I had a 1/7 on the right, right? Or a 1/8 or a 1/9 or a 1/10, whatever. I can achieve it by putting 1/13 times 7 on the left. And that's because 1/13 would get me to 1, but I don't want 1, I want 1/7. So by multiplying this number by whatever number I wish to have in the denominator on the right, I can achieve it. It feels like cheating.
So you're backing it in by knowing what you need and then just multiplying
That's
it
right.
by. Okay.
Very nice way of saying it. Now, in this case, the thing I needed was 3/8. So if we change 3/8 into 1/8 and 2/8, then I can get to the 1/8 by doing 1/13 times 8, which is 1/104. But then I can get to the 2/8 by doubling the 1/104, which becomes 1/52. Now we could also get there by thinking of it as 1/4, but they wouldn't have thought of it in that way. They would take whatever goal I had. If my goal is 3/8, they're turning it into 1/8 plus 2/8, and they're getting the 1/8 this way, and then they're getting the 2/8 by doubling it. But suppose I needed, for example, I needed 10/19, just for whatever reason. I don't need 10/19. But if I did need 10/19, my way of getting there would be to get 1/19 by doing think of 10/19 as 2 plus 8/19, because I break up the 10 into like powers of 2. And I would do this I'm not happy about using these large numbers, but since I'm already too deep into this, and it is good to show like different examples. So I would put 1/347 on the left, but 1/19 is not what I need. I need 2/19 and 8/19. So I would then double the 1/19 and double it again and double it again, although they wouldn't be writing it this way with the 2, the 4, and the 8, but I am going to for the purposes of instruction. This is also not so good because the 314 was odd, and I would have to use the 2/n table to get to 2/19, to get 2/347, which I don't even have. So this is a bad example. We don't have the mechanism to finish it. But
yeah,
for our purpose,
could you pick
Yes.
just a simpler one? I think the 10/19 was too big of a jump from the 2/3 because this seems like it's got more tricks than what you just did. You know what I'm saying? Because I thought I had it. And now,
absolutely.
yeah, because this one got a little
Let
crazy.
I agree with you. So let me go like this. Imagine I didn't need 10/19. I needed I have to multiply the sorry. This was a 13 here. I don't want to do 13 times 19 because I'm going to get an odd number. So imagine I needed 10/14. the way I would get to those 10/14ths would be to go through 1/14, 2/14, 4/14, and then 8/14. And I would use the 8 and the 2. Now the 1/14 would come over 1 over 13 times 14. Let me get that for you. Which is pretty large, which is 182. Now I could double that by changing it to 1 over 91. But now I would run into a problem again. You know, you can only divide this in half so many times until it eventually is going to turn odd. So eventually it turned to an odd one. So to go from 2 over 14 to 4 over 14, I have to look up what's 2 over 91 on the chart. And it's a tremendous thing. You know, I'm just going to say, you know, 1 over something, 1 over something, 1 over something, 1 over something. That would be from the chart. And then I would have to double. Anyone have the 2 over n chart handy? Want to say what 2 over 91 became? Because that is on the chart.
1 over 70 and 1 over 130.
Oh, wow. So did you say 70 and 130?
Yes.
Oh, okay. So that actually works out really nicely because since those both had even denominators, I could double those by taking half. So to get the 10 over 14, which was 2/14 plus 8/14, it would be 1 over 91, 1 over 35, 1 over 65. It gets pretty hairy in that way.
Yeah, sorry.
It's so
again.
bad that I'm not.
You're looking to get 2 over 91, right? So what, you're multiplying that by 2, and then the 2 over 91 is 1 over 70 and 1 over
No.
30.
I was only, that 2 over 91 was because, no, I was trying to get 4 over, I was trying to get 4 over 14. I had 2 over 14 was 1 over 91.
Right?
So 4 over 14 had to be 2 over 91.
Right.
So I had to look up what's 2 over 91 on the chart so I would know what to put right here. And that was only a vehicle for getting to 4 over
Right, but normally you go from 1 over 91 to half of 1 over 91, but you didn't do that. You doubled it. You doubled. All right.
I was done. No, I had to double it because my real goal is the stuff on the right. I was trying to get 10 over 14, which is 2 over 14 and 8 over 14. I was able to get 1 over 14 really quick, but I had I needed 3 more steps because my goal was 10 over 14. So I had to double to get 2 over 14 and double to get 4 over 14 and double to get 8 over 14. So I could combine the 8 and the 2 to get 10 over 14. But on the left-hand side, when I turned the 1 over 14 into 2 over 14, I had to change this 1 over 182 to 1. So I divided the 182 by 2 because that's how you double an even unit fraction.
Can I ask?
But then, no, yes, you can ask a question, and it's not going to be a dumb question.
You have 10 over 14 instead of 5 over 7 because you wanted an even number. When you had 10 over 19, no, when you had 10 over 19, could you have done 20 over 38 to have an even number too?
So that's a good question. That, it really wouldn't save you that. Yes, the answer is yes. It wouldn't save you that much time because all it really saved us is the 182 was even, so we got to divide that by 2. But we were out of luck on the next step. So yes, you could do something like that. And let me tell you, the Egyptians would sometimes take a fraction like they would take a fraction like 5 over 10, and they would actually change, maybe 5 over 10 is not the best one. I'll say 3 over 10, and they would actually change it to 1.5 over 5. So they were really comfortable with fractions over fractions. So they weren't always even caring about the denominator being even. So, but yes, in answer to your question, we could have doubled that. I made up this example as like an instructive example to show how when you get stuck in a problem, like, uh-oh, how am I going to get 3/8? You could always get there by getting 1/8 and building your way back up to whatever thing you're trying to get. But it can get pretty ugly because the 2 over n chart is, see, previously we only used the 2 over n chart on the right-hand side. Up until now, the 2 over n chart was a vehicle for doubling fractions on the right-hand side. But this was an example where the 2 over n chart was needed on the left-hand side because I was doubling unusual unit fractions on the left. And I had to do it over and over. So I had to make them into unit fractions so I could double those by potentially using the chart. Although this one worked out kind of nicely.
So
I'm gonna
Professor,
write-
really summarize this. It's the recognition that you need something like 10/14. You convert it to a unit fraction because that gives you that divided by the divisor, and then you just start doubling so that you can equal back to like the 10/14, right? By summing them up. Is that right?
And I didn't turn it into a unit fraction actually though. I turned it into a sum of fractions that had powers of 2 in the numerator. So
Yeah, but I'm talking about the right side. You wanted that 1/14 value that
oh,
you can.
yes. We needed the 1/14. That's right. You're exactly right. We needed the 1/14 so that we could build up the 2 and 8, which would get me the 10 that I needed.
So the oddity
It's pretty
here compared to last session is that you're doubling the right to get the left side to work out, to get the answer.
That's right.
Okay.
That's right. Now, this question, just so you know, this is not a question that would be on the final exam. This is a question I wanted to show you because I want you to appreciate the sophistication of the Egyptians. And if I just show you their like easiest questions, we might think, okay, they doubled and halved and doubled. But when you see a question like this, you're like, okay, they really would not shy away from very sophisticated questions. But this question is not going to be on a homework assignment. But mathematically speaking, I hope that if you think about it enough, you're good that by multiplying 13 times, that by multiplying 13 times 14, I would have 182, which would mean that I would have 1 over 182 on the left would get me 1/14 on the right. Now, good news for you, because this question took a while, I'm going to skip the even harder question I was going to do and skip right to something that's a little bit easier. Okay, so big thing for today is that actually I'm going to switch something, the easiest thing of all. I'm going to do the Egyptian geometry first. That's a little break. So let's type in. So people say that, the Egyptians needed geometry because the river would overflow and it would wipe out all their property lines. And they would need some kind of understanding of geometry to redraw the property lines. Also, for taxation, if somebody had an unusual shaped piece of land, the people in charge would have to know what's the area of this person's trapezoidal shaped land. So for these reasons, it's speculated that they needed to know various area formulas. Now, Babylonians certainly knew area formulas also. So if you look at this question, not this one, Question 49 in the Rhine Papyrus is just find the area of a rectangle. So let's just mention that they knew area equals base times height for a rectangle. That's all. That's one of our quick things for today. And they did it in this case. They showed they multiplied 1,000. They multiplied 100 times 10. I'm not quite sure what's going on here with 1,000 and the 10,000 and the 100,000. Well, of course, I can see what they're doing here. They are doing some conversion of measurements, but we are not going to have to memorize their units of measurement. So for our purposes, this is their way of saying that a rectangle that has dimensions 10 by 100 has an area of 1,000. And this should make everyone feel a little better if you're getting nervous about the unit fractions and the crazy division. Question 51 in the Rhine Papyrus shows that they
Professor, can you go
knew-
wait on 1 minute at problem 49?
Yes. And you don't have to worry so much about what they're doing here. I just wanted you to know that they did have the area of a rectangle is base times height. Now, question 51 shows that they knew that the area of a triangle was base times height over 2. They actually wrote it as base over 2 times height, or they thought of it in that way. So in this question, they're saying that it's 10 and 4. Sorry, it's 4. It's funny, they say side of 10, but they really mean altitude of 10. It's not that they're not literally saying 10 is one of the sides, I don't think. So this isn't drawn to scale. But you see, they say take half of 4. That's funny. To get its rectangle. They're basically saying, this is kind of neat, because the answer to this question is 20, which is 4 times 10 over 2 is 20. So let's start by just saying that they know the area of a triangle.
I mean, it's been a while since I took math, but isn't that what we do now? Like 1/2 times base times height?
Oh yeah, but just that they knew it.
Okay,
Oh,
all right.
you're wondering why? You might be wondering, what am I getting excited about?
Well, I'm just
I'm getting excited about the word rectangle there,
okay.
because what they're kind of saying, when I look at this, they're kind of saying that if I have this triangle, they're saying that there's a rectangle that has like half, this is a rectangle that has like half the height of that triangle.
Gotcha.
And I like that, because if I go like, it's not that obvious that this rectangle has the same area as the triangle. If I take a random triangle and I take the height and I kind of bisect it. Nowadays, we know area of a triangle is 1/2 base times height, but it's kind of sophisticated. Here's what it makes me think of, because I've seen things like this before. If I draw this line down the middle, you can see how this piece is kind of equal to that. And maybe this piece, if I drew it to scale, would be equal to that. And it would show that that rectangle has to have the same area as the triangle, because the rectangle is formed by this like trapezoid plus these 2 triangles, whereas the triangle is formed by the same trapezoid plus 2 equivalent triangles. This is speculation, but this is what these historians would be doing when they see the word rectangle. They think, there's like a clue going on. You know, they didn't just say, take half the base and multiply by the height. They wrote the word to get its rectangle. So it's like a clue. You know, we have so little clues about what were they thinking sometimes, especially, you know, when we see their algorithms sometimes. So anyway, I'm just having fun to speculate. For our purposes, I want you to know that they knew area equals base times height for rectangle, and they knew area of a triangle is 1/2 base times height.
Cool.
Question number 52 in the Rhine Papyrus shows that they talked about what they called a cutoff truncated triangle of land. Well, that is their way of describing a trapezoid. And they had the formula. They're describing this. They say it's 20 in its side, 6 in its base, and 4 is its cutoff line. They're basically saying that the bases are 4 and 6, and that the height is 20. Now, I didn't draw this, you know, to scale. And the formula is 1/2 B1 plus B2 times height. And they describe it very well. Add its base to the cutoff line. It makes 10. 4 plus 6. Half of 10 is 5. And then it says, in order to get its rectangle, multiply 20. In order to get its rectangle, multiply 20 times 5. So in this case, it's 1/2 of 4 plus 6 times 20, which is 5 times 20 equals 100. It's funny because they say 20 times 5, it makes 10, but they mean 100. They mean 100 of whatever their unit is, but it's 10 of a larger unit.
Hey, Professor, I'm sorry for a lot of questions, but is the
I love these questions.
Okay, thank you. The italicized version, is that actually translated out of ancient Egyptian and then the regular type are interpretation or instructions?
No, it's all translated. I think
Oh, it is.
I think the italics is just to distinguish like the question versus what they
instruction.
put in as their explanation.
Okay, cool.
No, the Rhine Papyrus, this is a full translation of what they actually have. And I actually put into the Google Classroom a link to the entire book, which is 85 questions, all detailed explanations, plus an introduction chapter that's 65 pages that explains pretty much everything I know about Egyptian math in that 65-page introduction to the translation.
And just as context, that we've decided that's a textbook, right? The Rhine Papyrus.
Yes, it itself is a really nice collection of these 85 questions that has like everything that they so much studies on there. I've been through most of the 85 questions actually. Like every time I study this Rhine Papyrus, I try to pick up like a few more questions. Some of them are really, really hairy. Like that division I just showed you. There was one where the answer had like 12 fractions in it.
Wow.
Okay, now here is one of the most interesting questions in the entire Rhine Papyrus. So let's take a look at what's going on here. What am I doing time-wise? Yeah, so we're going to take the break. Take a break at 11. This one's really, really important. Area of a circle. Example, a round field of diameter 9. What is its area? So this is big. This is like a huge moment in Egyptian math. So nowadays, we know the area, actual area, is pi r squared, which in this case is pi times 4.5 squared. So 3.14. So the actual area, by comparison, is about 63.62. That's the actual area by modern. Now pi itself was not discovered, invented until Greek times. We're going to learn about Archimedes in 250 BC, coming up with pi and using the formula pi r squared. But for thousands of years before Archimedes nails down pi as 22/7 approximately, other cultures did questions where they approximated the area and the perimeter of circles. That does not mean that they had pi, like an idea that there's some like ratio between the circumference and diameter. And that's okay. They had a formula for area of a circle. And let's see what their area, what their formula is. They got 64, which is not, the correct, it's not the exact answer, but it's a pretty good answer. It's off by like about 6% off. So what was their algorithm? Well, their algorithm says take away 1/9 of the diameter and multiply 8 times 8. So what they did, this is what they're saying, they said 9 minus 9/9 equals 8. And then they squared 8. So their formula is d minus d/9 squared. And this is very important because when I make the final, and I talk about this final a lot because it's worth 40% of the grade, and I used to not talk about the final so obsessively, and students would be doing the homework, but then on the final, there'd be a couple of students who would get like a 20, out of 100, or 15 out of 100 on the final. And well, they may have failed the course or come pretty close to failing the course. So we want to make sure if here's a formula, d minus d/9 squared. That's a formula that you're going to want to memorize. It's certainly an easy formula to apply once you know it, but that's the kind of question I like to ask on the final. It's a perfect question to ask on the final because it only takes a minute to solve the question, I'll tell you.
Professor, I had the same question like Vanessa had. Is it always d/9? Or is it depending, depending on
excellent, excellent question. It is always d/9. That okay. 9.
Thank you.
And questions like that show that you're thinking, okay, wait, is that 9 because the diameter was 9? Do I always divide it by itself? No, it's always going to be divided by 9. So, for example, if the diameter instead was 18, we would do 18 minus 18/9, which would become 16. And then you would do 16 squared. I'll go like this. So it's always over 9.
I know I'm going to probably do a rabbit hole, but why did they pick 9? Was it like just a number that sticked out to them?
And if we're going to talk about that now, because having an algorithm is great, but then you have to start trying to wonder why Why d minus d over 9 squared? How would they know that? Where would they pull that from? Some people I see combine these and say 8 ninths d squared. I personally don't like that. If you say that formula is 8 ninths d squared, you'll get the same answer, but you're losing something in that. You're losing the d minus d over 9 is like a clue. When you combine it into 8 ninths d, of course, 8 ninths for them was would be a hard fraction to write. But I like this formula. Now the question becomes, where does this formula come from? So one speculation is that usually when there's these formulas that approximate the area of a circle, usually those things are exact areas of things that are not exactly circles. So there's one speculation that maybe they were comparing, saying, well, this circle is kind of like this octagon. And if the diameter of the circle is d, each of these little squares would be d over 3 by d over 3. And we can see there's 1, 2, 3, 4, 5 full squares plus 2 more, because this is half of the square and this is half, and this is not a regular octagon, by the way. This side is smaller than the diagonal is times the square. It's a 45, 45, 90 right triangle. So this octagon thing's area is 7 ninths. Sorry. Each of these individual things is d squared over 9. So it's d squared over 9. Sorry, it's d over 3 by d over 3. Well, that's not the same thing as 8 ninths d squared, which is what their formula is. So then some people said, well, maybe they saw it was 7 ninths, but they also saw that this this octagon thing is actually not exactly equal, and that the area needs to be a little bit bigger because we need these little circular arcs added in. But then again, we have to take away these, there are also some pieces like stuck outside that are counted in the area. And this is all speculation that they just changed it from 7 ninths to 8 ninths to just account for the fact that 7 ninths was a little bit too small and that 8 ninths was more accurate. I have a whole article with like various theories about how they would have come up with this formula. This is not, to me, the most convincing argument for this formula. The most convincing argument comes from this picture. And by the way, I posted on the Google Classroom a PDF that has this sort of slide deck, all the questions plus all the diagrams. This is my favorite explanation of this formula. Again, it's all speculation. The idea is this. You can take circles, small circles, and rearrange them into, like, if I take 7 small circles, you could do this with coins. You could rearrange 7 circles into like a single hexagon looking thing, which looks kind of like a circle. So these 7 small circles kind of add up to one sort of big circle. But the number 7 is not a perfect square. So if you add more circles in, you can get real creative And here is one way. This picture is a pretty famous picture, like a speculation picture. They rearranged through some kind of trial and error process. Maybe they tried to if you use a perfect square, like you try with 9 circles, well, 9 circles, you can't make something that looks much like a circle. And you try again with 25 circles, you know, you literally like take 25 coins and try to arrange them into a big circle, and you can't. And then you try again with 36 circles, and you can't. And you try again with 49 circles, and you can't. But then you try again with 64 circles, and you manage to create this thing. 64 circles getting rearranged to becoming a circle. And that circle, that big one, you can kind of see, I'll erase here, you can kind of see that the diameter of that circle is kind of like 9, because you can see across the middle, see those nine yellow, orange. Well, you can take these same 64 circles and rearrange them into an 8x8 square. So the general rule would be 8 squared is the same thing. Well, how does that compare to the 9? It's 9 minus 9 over 9. It's 1/9. This 8 is not equal to 9. It's 9 minus 1/9 of it. This is total speculation, but it's my favorite explanation of this formula. It's real clever that 64 circles can be rearranged. And maybe if they couldn't rearrange 64 circles and it required 81 circles to make something that looks like a circle, they'd have to use a different formula based on that bigger thing. I wonder what the next, if I put another layer of circles kind of outside of this, I would get a bigger one. Oh yeah, but that bigger one would unlikely to be a perfect square.
But
So
this
you'd have
is
to
for-
keep adding layers.
This is for a circle of a diameter of 9. What if, what do they do for larger circles or smaller circles?
Well, once they know, no, they can't draw this picture again. This picture gets the general idea that a square whose side is 8/9 of the circle
Right.
would have the same area. And then they can say, well, now if the circle has, if it's not a multiple of 9, I have a circle with, 5 as my diameter, then it's 5 minus
5 over 9. Right.
minus 5 over 9 squared.
Right. Right.
So they figure out the formula one time, and once they have the formula, then they can apply it. So for our purposes, though, you definitely want to know the formula that the Egyptians had for the area of a circle.
How close was
As
it?
far as the 6% off by 6%. No matter what the diameter is, it's off by 6%. Now, some people, and if you go, you know what? Let me do this. I've been avoiding, because my iPad's I'm not able to switch back and forth the way I used to, because I got a replacement iPad. But all I have to do is click this, and I'm able to get to this page. Okay. Thumbs up if you could see can you see the screen now, or could you see nothing?
I only see
No.
last off by 6%. That's all I see.
Ah, okay. Okay. So does that mean, I guess that means that this window needs to be over here. Okay. Hold on.
Now we see it.
Okay. Now I'm going to show you something, an example of people when they analyze historical math
Digo, canta tão bom.
tablets
Jadi kurang nomor
How some people get, oh wait, here you go, I'll mute. How some people have gotten too optimistic about analyzing historical documents, like the Rhine Papyrus, like Plimpton 322, not being a trig chart, but being, you know, a student thing. And in the history of math, the most common example of somebody giving credit to a culture, and I'm not going to say the culture doesn't deserve the credit. It's more, we don't need to say they invented something they didn't invent if it's not true. And what I'm talking about here is, if you go, you don't have to, you can just look at my screen, but if you go to in Wikipedia, and in Wikipedia, you look up one of the more, you know, pi, it's got to be one of the more popular entries in Wikipedia. Now, Wikipedia, of course, is crowdsourced thing that's just made by people, you know, that edit it. I've actually thought of going in and editing this page, because we say here, it's approximately this, squaring the circle, thousands of years have attempted, and then it says ancient civilizations, including the Egyptians and Babylonians, required fairly accurate approximations of pi for practical computations. That's not true. Also untrue is, hold on, where is it? I'm looking for, hold on. I'm looking for a place where they're saying that the Egyptians had a specific value of pi. Where is it? There should be some kind of chart that has like different values of pi over the years.
Just Control F and type Egyptians.
Good idea. Here we go. Thank you. Based on the measurements, no, this claim is that the earliest written approximations of pi are found in Babylon and Egypt. This is not true. Both within 1% of the true value. In Babylon, a clay tablet had a geometrical statement that by implication treats pi. And then it says in Egypt, the Rhine Papyrus dated around 1650 BC has a formula for the area of the circle that treats pi as 16/9 squared. Now look at that. Again, Wikipedia is not, you know, it's just a thing that was crowdsourced, but, you know, this is really bad. But let's see why they're saying that, and then we'll see what's going on. 250. So, and by the way, if I go elsewhere, ancient approximations of pi. A brief history of pi, explanatory. This is just some random one. Just want to show you that someone's going to say that they had the Egyptians calculated the area by a formula that gave the approximate value of 3.1605 for pi. This is not true. So let me tell you what is true. Let me go back to the iPad. Okay. So what is true? Well, it's true that if you take d minus d/9 squared and you rewrite it as 2r, diameter is 2r, minus 2r over 9 squared. And you change that to 18r over 9 minus 2r over 9 squared equals 16 over 9 r squared equals 256 over 81 r squared. It's true. And 256 over 81 is equal to 3.16 approximately. That's true. So it's true that their formula gets you the same answer that you would get if you did A equals 256 over 81 times r squared. But they didn't think of it that way. Pi, refresher, pi is the ratio between the circumference and the diameter. And it turns out that, 1, 2, 3 diameters just isn't enough. So we need a little bit more. And C over D is approximately, 3.14, which is approximately 3 1/7. And that's true. So circumference equals pi times diameter, of course, because that's just what pi means, how many diameters fit around a circle. And then later on, they figured out that pi is also involved. Archimedes figured out that that same pi, that 3.14, was also involved in the area of a circle. But the Egyptians did not say, A is pi r squared, and I just wish I knew what pi was. That's not how they thought of it in any way whatsoever. They needed a formula for area of a circle. They came up with d minus d over 9 squared, and that's all they did. And it's great. It's actually off by 0.6%, not 6%, by 0.6%. They deserve credit for that. That's great. That's a great formula. But we shouldn't be saying that they were thinking pi was this number. Oh, if we only knew what pi was, and we think it's 256 over 81, which is 3.16. So when Wikipedia and this other web pages and all over say the Egyptians thought pi was 3.16, the Egyptians did not think pi was 3.16. They had no idea that there's this constant that's the ratio of the circumference to the diameter, and that same constant, if you multiply by the square of the radius, gets you the area of the circle. They did not have that at all. So to say that they had it and that the Egyptians thought pi was 3.16 is giving them, I'm not so upset of giving, I like giving the Egyptians credit. I'll give them credit for these unit fractions and the 2 over n table, and it blows my mind when I'm trying to calculate out 2 over 13 with it, and that they were able to do that. But you don't make up a thing that they didn't do, because that's lying to your students. That's lying to, that's not history anymore, saying the Egyptians knew that pi was 3.16. So I get very frustrated when I look at Wikipedia. They said that the Babylonians had something that suggested a value of pi of 3.18, because they also had some kind of algorithm for area, and that they should have said, what they should have said is the Egyptians had a formula for the area of a circle that is equivalent to saying 256 over 81 r squared. They could say that if they want, but do not say the Egyptians thought pi was 3.16 and they were just so close. They had a formula for area of a circle, and it's a great formula.
But it's cool
Okay.
that like they didn't have a concept of pi and they still had a formula that was so close.
Yes, that's right.
Yeah.
We don't have to say, oh, take it away. Oh, give. So so I love the Egyptian math. It baffles me, It's just, I don't like to see it misrepresented and the history of math represented on Wikipedia. So that's just a rant I have.
I'm sorry.
Because I have. Yeah.
Because I was just going to say they also said the Babylonians. So did the Babylonians have a concept of pi?
No, they also had some kind of an algorithm some kind of an algorithm. I think it had a square root involved in it, like the square root of 10, maybe. That the square root of 10 is like the area of a circle, which is the 3.18. In the Old Testament, there's a reference to there's a reference to a construction of something, and they said there's this thing and it's 10 cubits across and 30 cubits around, and people said to that, oh, in the Bible they say that pi is 3, and then some people say, well, now we don't believe the Bible because it said pi is 3. Well, why would anyone say 31.4 cubits around? You're writing a book that, it's an approximation. And then someone else goes into the Bible and shows that if you look at the Hebrew letters more carefully and interpret them in a different way, then they have an estimation of pi that's very accurate. So we shouldn't read into this stuff. Pi is not officially a thing until 250 BC, when Archimedes defines the ratio of the circumference and the diameter, and then also shows that same pi is involved in the area of a circle. Up until then, area in circle and perimeter of circle weren't considered to be like so highly related. Okay, well, that's my pi rant, because in history of math, including like a lot of books, obviously on that website I showed you, that was someone trying to teach history of math, and they're saying Egyptians said that pi was 256/16, and it's definitely not. See, I could see myself, I won't, but that would be a final exam question. True or false, the Egyptians thought pi was 256/81. But I don't, every question on the final is a math question.
Hey, Professor, is there a circumference formula that we should be aware of for the test, or is it just going to be an area question?
Just an area. I don't see any reference to a circumference in Rhiine Papyrus or in the Egyptian math. Of course, the area is real important. They want to know how much land does this person have so I could tax them properly. Whereas the perimeter isn't quite as important. Certainly, all cultures would know that it's about 3 times around. You just by measuring and taking steps. But no, the idea that it's any closer than 3 times wouldn't have been too important to them.
Okay, thank you.
Okay, now let's look at problem 44. Problem 44 shows that they had formulas for volume. And they knew that for a rectangular prism, the formula was length times width times height. So they have a 10 by 10 by 10 rectangular granary, and they get 1,000. Then it's funny because then they convert it into a measure that they have that's called hecats, which is apparently 7, you multiply by 7.5. But instead of multiplying by 7.5, they multiplied by 1.5 and then took 1/20th of that and then did some other stuff. But I'm not interested in you memorizing their units of measurement. So let's just say for problem 44 that they were aware of the volume of, and it's the same formula that we use now.
I'm a little.
So the only formula. Yep.
I'm a little confused by at its half. It makes 1,500. Why would they do that? So I got the volume. It's 1,000. Why does it?
Well, they're trying to multiply it by 7.5 eventually, but apparently they have another unit called KHAR. So if you multiply 1,000 times 1.5, you get 1,500. So apparently, now this doesn't have any units on it, the 10 and 10, but it's just whatever unit they have, it's implied, I guess. So they multiplied 1,000 by 1.5. Add its half means it plus 1/2 of it to get 1,500.
Is that because they like that number 3.5 because it's the reciprocal of 2/3 maybe?
They're really good with their 3.5, with their 1.5. Yeah, they're 3 halves. And then they take 1/20th of 1500, which makes 75. And then they basically multiply that by 100 to turn it into 7,500. So nowadays we would just say, oh, take their 1,000 and multiply it by 7.5. But their process for multiplying by 7.5 is times 3 halves, times 1/20th, and then times 100. They're more comfortable with timesing by 3 halves, and they're apparently comfortable with taking 1/20th of something. 1/20th of 1500 is 75. Keep in mind, 1/20th is kind of like a half.
It looks.
So they really managed. Yes.
No, I was just going to say Tina made a good point in regards to the conversion of units. So they're converting the volume, 1,000, into the units in regards to how much grain is in the box. Like, that was my question. Like, why are they doing this? You got the answer already.
Yeah.
So.
Oh yeah, no, it's a conversion into their units, their hecats. So yes, this is some kind of conversion factor, which you won't need to know at all. I just find it kind of like fun to see that nowadays it's times 7.5. That gets you from your volume to these hecats. But back then, timesing by 7.5 was done with the things that they were experts at. 3 halves times basically 1/10, 1/20th times 100. That's what they do to get multiplied by 7.5. Times by 3 halves, times by 1/2, times by 1/10, times by 100. Now, problem 41 is kind of surprising to me. It's the volume of a cylinder, and what's not surprising is that the formula is area of base times the height. So nowadays, it's pi r squared h. But then it was d minus d over 9 squared h. The only thing that's surprising about it is that it's problem 41, when problem 50 was where they introduced the area of a circle. So they introduced the area of a circle in this volume question as problem 41. Well, if I wrote the Rhine Papyrus, I would absolutely put the area of the circle before I put the volume of a cylinder, which depends upon the area of a circle. But so their volume, is d times d over 9 squared. And here they explain. So if d equals 9, a equals 640.
Frankly, it's
9
amazing
minus-
how close it is to modern geometry, right? I mean, seriously, I mean.
It's off by it's off by less than 1%. So d minus d over 9 is really good. Like d minus d over 10 was going to be too big, and d minus d over 8 was going to be too small. So it is pretty amazing. It's very good. And there's a lot of speculation. I just showed you 2 theories, but I have a paper a 20-page thing that I downloaded that has more theories of how they might have come up with this formula. Now, I love the formula d minus d over 9 squared. It has a really good chance at being a 5-point question on the final exam.
Would we be expected to write it out with the 2 columns, or we just need to know the formulas?
Oh, so on the final, for this question, you'd be able to just type it into a calculator, d minus, but there'll be other questions where I might say, show how the Egyptians would multiply such and such. So if I say, show how the Egyptians would multiply this, for that, but if I just ask a question about, like, here, what's their algorithm, we can use modern multiplication to use their ancient formula. So you would not have to do the multiplication of 8 times 8, you could just do 8 times 8 is 64. You wouldn't have to. This is their way of doing 8 times 8 is 64. And this is their way of doing 64 times 10. On the final, you wouldn't have to show that. You wouldn't have to either. I give you something to do, and I would say show the Egyptian method of solving this. But for this, it would be use the Egyptian formula to solve this, but you don't have to use the Egyptian method of calculating once you know what to do, what numbers to multiply and divide. Good question. This is a good stopping point. Let's take a 10-minute break now. I'm going to try to get my technology fixed because something's not working with it. So I'll see you guys in 10 minutes. Okay, everybody. Good news. I used that break to get my computer system working again. And now I can see everybody again. Okay, so sorry if I wasn't as sharp as I could be. I think that was 10 minutes. I started the break like a little bit before, 11, so it's 11:06 now. And now I can also bring up the dashboard. So if you go to the, you could be putting in your, as I go through these questions, just to show that you're following along, you can put the answers into the Desmos thing. Each of these questions, let me just see how. Let's see if people are logged into it. That's how I check for like participation. Are you following along by typing some stuff into those boxes?
Oh, so what question are we on in Desmos? Because I see 12 questions here. First one, find unit fraction decomposition of 2/13.
We did that one. Hold on. I think I skipped over 3 questions, and then now we're like cycling back. So we're now doing questions 3, 3 and 4 and 2. We only have 3 more questions. Oh no, sorry. We're on question 11, 12. So we're going to do 11. All we have left is 11, 12, 3, 4, 2. I'll make a note here.
Thank you.
Okay, left to do 11, 11, 12, 3, 4, 2. Yeah, you can you can put these in when you're able to. Oh, here, let me know. Okay. Oh, I'm so happy I have my system working again. So let's look now at question 56. And by the way, I put into here, into the Google Classroom, I have a link here. One says this PDF. That's actually a book, full translation. I actually own this book, or at my school we have 2 copies of it, and it's really good. Tomorrow we're going to start a new culture. So this is the end. This is as far as we'll go. But you could do a whole course just on the Egyptian math. Okay. Pyramid. Well, we're talking about Egypt, so not surprising. There's questions about pyramids. Now, it says here a pyramid is 250 cubits high, and the side of its base 360 cubits long, and it has a new word for us. What is its second? Well, this is something new. Now, if you find this document, you're like, I don't even know what second means. So how am I going to do that? Well, they give some explanations. They say take 360 divided by 2, it's 180. Then they say it says multiply 280 so as to get 180. So that's 250 basically divided by 180, or 250 times what equals 180. So they're dividing 180 divided by 250. And they get this unusual 1/2, 1/5, 1/50. And then they multiply that by 7. Hold on, where's the answer? I think I'll cut it off by accident. Hold on a second. The answer is supposed to be 5 and 1/25. 1/25. Now, at this point, we don't even know what a second is. So what is this thing? That's what I'm going to teach you. what a secant is. So if you have pyramids, here's a cross section. You could have pyramids that have like a big angle here, like a 70-degree angle, or like a 50-degree angle, or a 30-degree angle. And the secant is related to that. It's kind of like the angle, but not exactly. If there was a pyramid, that had a height of 7, altitude, and the base was 20, the secant would be 10. What the secant is, oh, well, sorry, I haven't told you what it means yet, but I just want to tease it a little bit. If the height was 14 and the base was 40, the secant would also be 10.
So secant doesn't change if you change the parameters, doubling it, tripling it. What if you have
That's-
it?
That's the same thing, because what a secant basically is, a secant is if you shrunk the pyramid down so that the height was 7, how big would half the base be? That's what that's basically what the secant means. So another way to think about it, let's have one where the height's not 7. Oh, let's use the example. In the Rhine Papyrus example, they tell us, this is question 56. They tell us that this is 250 and this is 360. Oh, am I? And they want to know what's the secant. So what you do is you divide the 360 by 2 to get 180. And we say to ourselves, okay, this 180, what would this 180 be if the 250 were a 7? So you could do like a proportion. I'll go 180. And you'll end up with 5 and 1/25.
Did they have any concept of trigonometry?
Well, let's see how are they thinking of this, and
So is this like a pie to them?
what, like a pie?
Yeah. Like
It's more like, it's very much related, I'm right, related to the slope.
Hmm.
In other words, the slope of this diagonal side is 180 over 250. No, it's 250 over 180. The reciprocal of the slope is 180 over 250. And the secant is 180 over 250 times 7. So the secant is very much related. So the bigger the secant is, let's put on a picture. So if I have 250, 180, should have made the 180 smaller than the 250. Second is equal to 5 and 1/25. But if it was a steeper pyramid and it was 250, 100, our calculation is 100 over 250 and then times 7. Which is 700 over 250, which is 3, which is 2 point something, 2, remainder 200. 200 over 250, 2 4/5. So here's our formula for second. Second is 1/2 the base, right? That was because the base is really the entire base divided by the height and then multiplied at the end by 7. Talk about the times 7 in a second, but that's our formula. We can actually see in the, let me leave this up for a second. We can see, so there's a formula for you. It's not a hard formula to apply. Here they explain, see, take half of 360. That's half the base. It makes 180. Multiply 250. So to get 180, that's basically saying 180 divided by 250 becomes this. And then they multiply by 7. Notice the multiplying by 7 is a measurement conversion because their unit of measurement was the cubit. Which was broken up into 7 palms. Now, so you could actually put your hand to measure a cubit, you know, by going like that. The palms didn't include your thumb, so each palm was equal to 4 fingers. So 1 cubit equals 7 palms, and 1 palm is equal to 4 fingers. We still use fingers sometimes. If you go back to the Old West and you want to get some whiskey, you know, yeah, you tell them, give me 4 fingers worth of whiskey. I don't know if you ever get to go to the Old West or not.
All right, so
Vanessa
just,
asked. Yes, just, oh, go ahead, Scott.
I'm sorry, just to rewind, the second equals 1/2 the base divided by the height, and then you take the second times 7 to get the volume, right?
No. The times 7 gets the second. There's no
Oh.
volume.
Oh.
1/2 base divided by height, and then
Yeah.
times 7. That
Okay,
is the
thank you.
second. Vanessa, this is also one. See, this would be a question about, do you know what the algorithm is? So you'd be able to use a calculator. You wouldn't have to actually, I would never combine a second calculation question with a use, you know, Egyptian multiplication with the 2/n chart. Either we have questions from last class, where we're using the 2/n chart and doubling and all that, or we're doing an algorithm. The only exception is we have one more algorithm coming today, and that one involves multiplication and division, and you would be doing that with the Egyptian multiplication and division. Now with this, so the thing about the second is that if I told you make a pyramid with, you know, second equals 10, what you would do is you'd be able to make your 7 palms with your hand, and then you would just use your palms to make 10 palms this way. So second is measured in palms. And it tells you, if I want to make a second of 10, my pyramid would have these dimensions, would be 7 by 10. So I could actually use this in a practical purpose to build a pyramid. I'm constantly needing to make something that's that angle, and using my hand, the second is measured in palms, because you'd be very easily able to just, maybe you have a stick that's already 1 cubit that you stick in the ground, and then you use your palms to make 10 palms. That's your second, and then I'm able to create my pyramid with a proper angle.
For the final, are we
So
allowed?
question.
For the final, are we allowed to
Say that
use?
again?
For the final, are we allowed to use notes?
No, you wouldn't be able to use notes. So, from today, you'd have the second, calculation, and you'd have the d over 9 squared. But there's not going to be so many formulas to like study and know, but you wouldn't be able to use notes for the final. But fortunately, they won't be more than, like, up until this point, if we get 1 formula a day or 2 formulas, there won't be that many. Now, question 57 is where they're telling you the second is 5 palms and 1 finger. That's the same thing as 5 1/4. So the mini pyramid would look like that. That's the. So then they ask, what's the altitude if the real pyramid with the same second has a base of 140? You could use any method you want. Personally, I would use a proportion, since you're going to use a calculator at the end anyway. So go ahead, calculate out the altitude.
Where'd the 7 come from?
Because the second means if the height of the pyramid were 7 palms,
Oh, gotcha.
half the base would be 5 1/4 palms.
Gotcha. Okay, thank you.
I'm sorry, the first triangle, what does that say for the altitude?
7. Because
Oh, the
by
second line.
making by making the base, half the base, equal to the second, the height will always be 7. Because that's what second is. Second is, if the height were 7, what would half the base be?
I have a question. Why are
Yes.
we dividing it over 140? Should it not be half of it, 70?
Oh,
I was gonna ask the same thing.
thanks a lot.
Okay.
Thank you. I was wondering why my calculation wasn't working out. 70. So that's 490 divided by 5.25. Thank you very much.
So because you know the second, you're able to calculate the height is what you're trying to get us to understand, right? And then
That's
apply
right.
that. height. Okay.
If we know the second and we know the base, we can find the height. And we get 90, 93 and a third. Now, they show their steps. They divide 1 cubit by the second doubled. You know, it's more complicated with what they did. I'm trying to even analyze it, which is 10 and a half. Where is that coming from? What did they do? They doubled the second, so they have 10 and a half, and they divided a cubit. That's strange though. Oh, so the second doubled is 10 and a half. And then they multiply 10 and a half. So as it's very confusing what they do. That's why I wouldn't do it that way. I permit you to use this proportion. 7 will always be the numerator. The second will always be the denominator. And this will be the altitude. And this 70 will be half the base, not the whole base, like I. So second is kind of like slope. It's a recipe for making a pyramid that has a certain, angle, that has a certain angle at its base. And that's very cool.
So you won't give us a problem where we won't have 7 in the numerators, you're saying?
Well, you have to have 7 in the numerator because the 7 is how they're converting from cubits to palms, which is
Right.
the unit of measurement that the second is in. So 7 will always be in that numerator because second is always cubits. If I don't change it, if I don't have a 7 there, I'm not using that's what gets me the proper unit. So I like that question also. It's just knowing what second means. It's kind of like, it's basically 7. I think I said that, I'll say it again. Second is 7 divided by slope. That's what the second is, 7 times 1 over slope. Now, nowadays we do slope as rise over run, but it so easily could have just been run over rise, and that a bigger number would be a smaller slope. But okay, so that is second. So what we've done today, so far, we reviewed a question about division, and it got really hairy. You remember that one? That was difficult. And then we switched over to the various geometry that they had: area of a rectangle, area of a triangle, area of a frustum, area of a circle. I went on a rant about people that give credit to cultures inventing pi when they didn't. Then we went into the volume formulas, which are our formulas except for this one, and then the second. In the last portion of class, we are going to look at a really cool, I think, interesting thing. Hold on. Not that. Oh, question in here. Hold on. Yeah, someone else asked about, these formulas. I know it's kind of weird. Some of you are math teachers. Well, certainly with math teachers, you teach a formula sometimes, but you have to memorize it because because it's easier if you understand the formula, it's easier to memorize. So like, it's not just like, okay, why do people need formulas memorized when of course in the real world, you can look up the formula on a reference table. That's the argument in favor of letting people use a formula sheet on a test. But on the other hand, if the formula has some kind of rationale to it, and it's not just, oh, they memorized the formula and it's just, the formula means nothing to them except they memorized it. But if the formula has some kind of logic to it, then forcing people to memorize the formula, of course, they could just memorize the formula blindly and not have any idea why the formula is what it is. But that's, that person might get the formula wrong because they didn't have any kind of logic to hook it onto. So that's why I feel okay, no, not letting you use a formula sheet on the final. So the question we're looking at is not this. This is the hardest question actually that I skipped over, might come back to. We're looking at question 25, sorry, Rhine Papyrus 25 and 27. Okay, page 3 and 4. Okay, I think you'll like this one. X plus X over 2. There's a series of questions, and these are very famous. If someone were to say what's the most important like things the Egyptians came up with, we'd probably say unit fractions, formula for area of a circle, and something that's called the method of false position. And it's used for answering a question like this: X plus X over 2 is equal to, it's not just over 2, just X plus, in this case, equals 16. Or just to write down both questions, so we have both of the examples. X plus X over 5 equals 21.
Whoa, okay.
Okay, questions like this, X plus X over something equals something else. These are a type of algebra questions that the Egyptians liked to solve. So let's look at X plus X over 2 equals 16. Now they had two different methods for solving this question. I'm interested in the second method, but I just want to show you. Oh, and they would say, you know, something plus half of itself is equal to 16. So one method would be to sort of like combine, and they would end up just doing a division. This is one way to do it. Basically, the modern method, combine X plus X over 2, which is 1.5 X. If you want to go totally modern, right, you go 3 over 2X equals 16, and then X equals 16 times 3 over 2. That didn't work. 16 times 2/3, I mean, equals 32 over 3. That's totally modern. We're not going to be allowed to do it that way. Okay, they have two methods. One of them would be to do this division, which this division is kind of annoying. If I tried to do this, 16 divided by 1 and 1/2, let's just take a look. Double, double, double. It's actually not too bad. I have 13, I have 15. I have 15, and I need 16. So half isn't going to be so good. Half of 1 is 3/4, is 1 1/4. So I jump to 2/3, which is actually 2/3 of 1 1/2 is 1, and I'm done. So they did have a method that just involved dividing, but that is not the method of false position. But I wanted to show you because there's going to be another question where they don't use false position. But today's finale is false position, and you're going to really like false position.
Could you just go back to that answer, please? You went a little
Yeah.
quick there. Please,
Yeah,
thank you.
agreed. You went a little fast.
Okay, so that one I turned it into a division problem, just 16 divided by 1 1/2, because this here is the same thing as saying if I do like common denominators, 1 plus 1/2 is 1 1/2.
I noticed you stopped doubling at 8.
Yeah, I stopped.
Okay. So why didn't you double to 2? Okay, well, just
Oh, so then I ended up with a division problem. Now that's what we practiced for homework over the weekend. Divide 16 by 1 1/2 by making the chart where you start with 1 and 1 1/2, and you start doubling until you get close to 16 as possible. But we didn't get to 16 exactly. We got to 15. We needed an extra 1, so we had to, in this case, use fractions.
But this is not
So
your
16
preferred
divi-
method, right? This
No.
is not your.
No, there's going to be a sneakier way of doing it. But I wanted to show you because they did do this. But this isn't the method of false position. I want to compare them. The method of false position is very slick, and it's really clever. You'll like it. It goes like this. Guess x equals whatever the denominator is. Okay, so you start by guessing. In this case, I guess that the answer is 2. What's so good about 2? Well, 2 is an easy thing to check. 2 plus 2 over 2 is equal to 3, which means 2 is not the right answer. It's not the same thing as 16. So 2 was too small. I need to multiply 2 by something to get the real answer. Imagine that the question, instead of being 16, can I just come over here? I don't know why I didn't show. Imagine that the question was not 16, but the question was 15. I should have shown this as my example. We'd say, okay, try x equals 2. This is a different question, easier. Try x equals 2. 2 plus 2 over 2 is 3, which is not 15. So someone want to type into the comments? So what is the answer? If 2 is not the answer, if 2 got me 3, not 15, what would get me 15?
10.
10. Why 10?
Multiplying 3 by 5 to
That's right.
to the 15, right? I mean, we have to divide 15 by 3.
That's right. Because 15, we're trying to get 3. We're trying to get 15, we only got 3. So if you divide 15 by 3, we get 5. So that means my answer was 5 times too small. So I multiplied 2 times 5 to get 10, which is the right answer. So what false position has is a guess, which is usually wrong, a division. You divide the number you want to get by what your guess led to. And then you take the result of that division and you multiply the guess by whatever I'm going to say the scale factor, I'm going to say scale factor. I don't know if that's the best thing to call it, but in other words, because 3 was 1/5 of 15, my original guess had to be 1/5 of the real answer. So let's come back here now. So now we have to do the division. 16 divided by 3, which see, it's not so bad. 12 plus 3 is 15. I want one more. Well, 1/3 gets me there, but the Egyptians would go there like that. So 16 divided by 3
The bottom
is
the bottom.
is, oh wait, I'm sorry, I made a mistake. Sorry, I'm doing something wrong here. 5, yeah, is sorry, why is this checked? I'm checking the wrong things. Let me highlight those. 3 plus 12 plus 1. So 16 divided by 3 is 5 1/3. And then finally I multiply 5 1/3 times 2. I like to, if I have a choice, I like to put the fractional thing on the left-hand side. I forget how the Egyptians would do this, like whether they thought of it as 2 times 5 1/3 or 5 1/3 times 2. It's always easier to multiply by an integer, so I'm just going to choose to do it that way.
You went from 15 to 17? Is that what you did?
Oh, so I had so over here I had 15,
Right.
and I wanted one more,
One more.
but I wasn't able to.
In the
I see what
previous,
you're saying. You're saying here,
in the
there's 2
previous,
you're wondering about.
you added 1 2/3. Yeah. Now you're doing 2 2/3.
Well, the thing on the left, I was doing a division problem, and I was trying to achieve a goal of getting the number 17, of getting the number 16, and I was 1 away from it. But the Egyptians wouldn't have jumped straight from straight to 1/3 of 3 is 1. They would have first done 2/3 of 3 is 2, and then done half of it. So I that's why this 2 is here. But this is a division. But this one over here is a multiplication. I'm multiplying the answer I got from the division by my initial guess. So you multiply 5 1/3 times 2. Well, when you multiply by 2, you're trying to get 2 on the left-hand side. And I get there very quickly by doubling 1, and now I'm at 2 and I'm done. The answer was 10 2/3. I don't even have to add a bunch of stuff together. So the difference is the thing on the right is a multiplication.
Right, but the thing on the
So
left,
double.
the thing on the left is the division. That's what I was questioning, because when you did the division originally, you didn't do the 2 2/3. You did the 1 2/3. So I was confused by that.
When you divide, you double until it gets too big. So once I did the 1 and the 4, I was already at 15. I can't double the 4 again. So I'm only at 15, but I have a goal of getting to 16.
Right.
So I need one more thing over here. So my way to get to that
Professor.
one,
Sorry to
Yes.
interrupt. Scott is being asked to be let back in.
here you go. Here you go. Welcome back. Sorry about that. Thanks for pointing that out. So you should look over, sometimes when you look at the division in the context of this problem, which has all this other stuff going on, it has a guess, it has a division, it has a multiplication. It can be pretty confusing when you see all that together. But if you look at last night's homework, if I said 16 divided by 3, that would be, a pretty easy example of division. The only weird thing is to achieve 1 by going through 2/3 of 3 and 1/3 of 3. That step's like a little weird, but since they do it, I kind of want us to not jump straight to 1/3 ever, but to get there through the 2/3. I think when you did the division for homework, you probably wouldn't have had trouble with that question. But I think when we put it into this larger problem with a guess and a division and then a multiplication, it does get kind of confusing when we do that. Now I would like you to try to apply the method of false position to the other question. Actually, I want to put you into groups for it. Okay, so here, where is it? X plus, I'm looking for x plus x over 5 equals 21. I'll put you into groups for 15 minutes about this one. This will be our last question for today. X plus x over 5 equals 21. Why isn't it? Is it not written anywhere? No. So I'll just write it here.
It's
So in
like
groups-
4 of the decimals anyway.
I got you. Now, I noticed in the last class, one of the groups did a very wise thing. They opened up the whiteboard on the Zoom, and then they were able to write on it, and other people were able to write on it. So yeah, you're writing with a mouse, maybe if you're not using a tablet, but let's give you 10, let's say more, because after this question, I'm just going to pop up the answer and be done. So I'm going to give you 15 minutes to talk to your neighbors about doing this question with false position. It's going to require a guess, a division, and a multiplication. Breakout rooms. Let's go into 5 rooms like before. I believe 1, 2, and 3 are for math teachers, and 4 and 5 are for math majors. Okay, see you in the groups. And I want everyone to go into a group, because to me, if you're not going into a group, you might just be kind of screen off, not really here right now. So everyone pick a group, even if you don't like going into a group. If you don't go into a group,
I don't see the options. Could you put me in a group?
here they go. Here they go. And some people need me to manually put them into groups, so I'm happy to do that. Anyone just want to call out their name and a group number, I'll pop you in there.
Professor, please don't bounce me because I missed something here because I got disconnected.
Okay.
Yeah, Professor, can you please say again the groups for the math teachers are
1, 4, and 5 for math teachers.
1, 4,
1,
5.
2, and 3 for 4 and 5 for math teacher, for math rats.
Thanks.
Math majors were supposed to be in 4 and 5, and math teachers in 1, 2, and 3. Did I say it backwards? Okay, Scott, what point did you get bumped off? Because I'll go over this with you again. Let me go back to the initial question. So the question is x plus x over 2. Oh, were you here when I did x plus x over 2 equals 15?
I got 15. That's when I got bounced out, because then we put 2 plus 2 plus 2 equals 15 was 3 equals 15, and that didn't work. So
let me do this one again. So when you put 2 in, you get 3,
right,
which is not 15.
Right.
So what do you do to that 3 to get the actual answer? you have to ask yourself, oh, 3, 2 is wrong because I don't want 3, I want 15. So what you do is you say, what am I off by? What factor was my guess off by? Well, if I divide 15 by 3, I get 5. So 5 was the factor. So then you just do 2 times 5, and out comes the answer.
2 times.
Had you
So it's
guessed, because 2 didn't work, but if I multiply 2 by 5, it will be 10 times 10 over 2 is 15, which is the right answer. So everything would get multiplied by 5.
Just
So
write it
there's a
down.
division. There's a division and a multiplication process. There's 3 steps: the guess,
Yes.
the division, and the
Division,
multiplication.
multiplication.
So
Now
you divide the goal.
Go ahead. Sorry.
You divide the thing you want to get by the thing you actually got. And then you multiply that answer by your initial guess.
So divide this, going back to the original problem, since you want 16, you divide that by 3.
Oh, forget it. Oh, so this 15 was like a new question, like an easier version.
Right.
And then I said, but it's not 15, it's 16. That 15 is not something we would like do in the 16 question. I just wanted to show that would be like, it would have been nicer if it was
Right.
15 instead of 16.
Right.
But our process, so here I have x plus x over 2 equals 16. So it's kind of annoying because when you put 2 in, you get 3, which is not 16.
Good.
So I have to divide not 15 divided by 3, but 16 divided by 3.
16.
And that's annoying, right? Because I don't want 15, I want 16. But 16 divided by 3 is an annoyance. Because that's kind of what we did for homework in the previous homework.
Right.
That's what it looks like when you divide 16 by 3, it's 5 1/3.
Okay. 2, and then 1/3 is 1. So what we're doing is, the second method is to go, once we figure out that it's 16 1/3 doesn't work, we want to come up with 5 1/3 by going back to the technique we learned over the weekend.
Well, we want to know how much was my guess off by.
Yeah.
So when it was 15 instead of 16, oh, that's easy. 3 times 5 is 15. But when it's 16, we have to divide to figure out what the adjustment factor is.
Right. All right.
When it was 15, it was obvious. Oh, I'm off by 5. But when it's 16, it's not so obvious. I'm off by 5 and a bit. That bit we get by dividing. See, when it was 15, we wouldn't even need to divide. We could just look at it and say, oh, I'm off by 5, multiply the answer by 5, and I'm done.
Right.
But if someone didn't know, oh, 15, 3 times 5 is 15, they would have to do it by dividing.
16 divided by 3 is 5 1. Now, once you get the 5 1/3, you go back to the division tree, right, or multiplication tree.
No. Now we multiply.
Yep.
2 times 5 1/3. Because the 2 was my initial guess, but it's also off by the same factor. So the answer I get for the division is the thing I multiply my guess by. Just like I did over here, I multiplied 2 times 5. 2 times 5 is easy. I do it in my head. Well, 2 times 5 1/3 isn't actually that bad. The Egyptians would do 2 times 5 1/3. Literally, they would just do 2 times 5 1/3 like that.
Gotcha.
And they'd be done.
So are we allowed to just take the division of 16 over 3 and said, since I divided by 2, just say 2 times 5 1/3, or
Well,
no?
do you mean to get the 5 1/3?
Yeah, well, no.
Because you wouldn't.
Don't we get the 5 1/3 because we took the guess, right, of 2 over 2 plus 2 equals 16. We come out with 16 thirds or 5 1/3. Are we able to take-
No.
Okay.
When we do 2 plus 2 over 2, we don't get 16/3. We get 3.
Right, but 3 equals 16, and then don't we turn that into 16/3 or
No, 3 doesn't equal. This is a not equal sign. I'm
Okay.
saying, uh-oh,
Okay,
I wish it equaled 16. Then I'd be done. Then my guess would have been correct.
but here's the
because-
thing, but when you, isn't 16 1/3 equal to 5 1/3?
Yeah,
But
That's right.
isn't that what we get when we did the multiplication table anyways? Because,
well,
Three
that was a division table.
okay, a division table, sorry. But
We
We
were
get the si-
dividing 16.
But
Go ahead.
yeah, but isn't there an algorithm here? Because it still works out, because your guess of 3 equals 16, if I divided that into under the 16, it's 16/3, it's just 5 1/3. Doesn't that still equal what you get out of the division table?
Well, let me do this. First of all, I'm going to erase the 16 from that step there.
Okay,
Okay, I'm going to leave it as just equals 3 and say, oh, okay, I
Okay.
got 3.
okay,
I didn't want 3. I wanted 16.
right,
My answer is too small. I'm going to need to multiply it by something so that when I plug in, I don't get 3, I get 16.
uh-huh,
So that's where, so it's not that 3 equals 16, right? 3 and
No.
16 are different numbers.
no, right.
And
I
3
get
is
that.
not equal to 16 over 3 either.
Right,
16 over 3 is what I was off by. I was off by my answer was too small.
right,
Can I go back to the one with the 5?
sure,
So,
sure,
Can I go back to this one?
Yep.
So let me erase the 15 here. I think this will be easier when I say here, okay, I got 3. I wanted 15.
right.
My answer is wrong. How wrong is it? By what factor? I didn't want 3, I
5.
wanted 15 to pop up. 5. How'd you get that 5?
Because you divided 3 into the 15,
Exactly.
yeah,
You did 15 divided by 3. So now I come over here and I say, oh, my answer is wrong. I got a 3. I wanted a 16. So what do I need to multiply everything by? What's the magic multiplier? You have to divide, not 15 divided by 3 is 5, but 16 divided by 3
right,
tells me
And the-
5 1/3. That's the magic number. That's what my answer was off by also, because the 3 was off by 5 1/3.
right.
You have to multiply 3 times 5 1/3 to become 16. So this 5 1/3 is 16 divided by 3, just like the 5 in this example
Mhm.
was 15 divided by 3. But it was so easy, we didn't even think about it. We were just like, okay, it's 3. I need 15, so multiply by 5.
Gotcha,
But in this one, it wasn't so easy. So I had to, on the side, do an actual full-on division to get 5 1/3. And that told me the magic multiplier that would not only turn 3 into 16, but it would turn 2 into the actual answer to the original question.
so I think I'm on the same page with you. My only question is, since you had 3 doesn't equal 16, but if you divided the 3 into 16, you'd get 5 1/3. Do you need to do the division table that you did on the side? Because you get that by taking the answer you want compared to what you got with the guess, which is 5 1/3.
That's right.
So do we need to do that division table, or can we just skip that?
How would you? Oh, I got you. So what would you do? Are you saying that could you just like kind of do 16 divided by 3? Old school, new school, 5
Right.
1/3, like that.
Yeah.
So okay, that is not so bad. Like I probably could have said you could do that. Like 'cause sometimes I say, it's not that important. But for
Right.
this question, I'm really fond of this question. And since
Okay.
we practiced division so much in the last homework, I'm gonna have us go ahead and do it. But
No, I
but
appreciate
yes,
that.
I like what you're saying. You're saying, what if I just, would it be the end of the world if I did this division by modern methods? I'm still doing false position. I'm still knowing the steps of dividing and multiplying.
Right.
Um,
Well, listen, hey,
I'm
I
tempted.
can do the, I guess I can do, I mean, listen, it's your class, you get to decide. I'm just saying, once I see the guess doesn't equal the 16, I know that number divided by the guess result is gonna be what I need out of
Yes.
the division table, because they equal each other. I mean, there's just no getting
That's
around
right.
it. You
That's
know,
right. It's just whether you divide by modern methods or Egyptian methods. And
exactly.
and in this question, I just get a kick out of that my students are doing like a false position,
Yep.
fully immersed, even
Yeah.
with the multiplication and division.
No, I
remember,
respect that. I respect that. So no worries. I just
throughout
wanted to
today, yes, throughout today with the formulas for area and stuff, that I'm
Yep.
okay with using a calculator for. But I have like a soft spot for this question. Okay, so really good. Now the group is working on x plus x over 5 equals 21. And
Yep.
why don't we, while we're together,
Yep.
why don't you do this question, and I will let you use modern division for it, just so I can see that you know the steps.
Sure. All right. So take the problem. So x plus x over 5 equals 21. So my guess should be 5. So I'm going to put 5 in.
Mm-hmm.
So 5 plus 1 is 6. 6 does not equal 21. Now, in my head, I would say the answer is probably going to be 21/6 simplified, which would be 3 and 4, 6, 18, 3 and 1/2, I guess. So, but now I'm going to go ahead and do the division table.
No, forget that for now.
Okay,
And now,
okay.
what would you do with that 3.5?
So I would say to myself, ha, I have to take the guess number times the 3.5. And that would give me 16. No, wait,
No.
yeah, 6. 5 times
You're
3
getting there, but... Oh, 5 times 3 and then 5 times 1/2.
was 16, right?
No, 5 times 3.5. Do 5 times 3 and then do 5 times 1/2 and combine them.
2 times 3. Oh, wait, could you say that one more time, Professor? Sorry.
Do 5 times 3.
Yeah.
And then do 5 times 1/2 and add those
Oh,
together.
yeah. There. So like 5 and 1/2. So that's 15. So 17.5.
And that's the answer.
Okay.
Now, the only difference between what you just did and what I'm going to ask you to do on the test and on the homework is this division.
Yep.
You're going to go like this.
21 divided by 6. And now I'm going to go through, and 1 times 6, 2 times 12, 3 times is 18, or no, 24.
Too big.
Right, so stop there. Good. Now I need to look at probably 1/2 and 2/3 are always good options. So 1/2 would be 3, 2/3 would be 4. Let me see what I got. And I needed to add up to 21. So
That's right.
2, 3, that's 19. That doesn't work. 10 is 22. Oh, here we go. Yeah, 12. Oh, so it's going to be, yep, 6, 12, 18, and 3 is 21, which is what I want, which means I go over to the other side, 1 plus 2 plus 1/2. I did it. Woo! I got to tell you, I feel like this is really a class of puzzles. This is, yeah, I'm loving this. All right, so 1 plus 2 is 3. And then you just add the 1/2 because that's a fraction by itself. And there it equals out. Now I take the 3/2 back and I recognize that my guess scale was 5. So I take the 5 times the 3.5 5 times 3 is 15, 5, it works out perfectly.
And that's right. Hey, everybody. So, oh, let me reshare my, I think I have to share.
No,
my
I just
screen
wanted to
again.
show everybody something real quick.
Oh, yeah.
So if you were to do the normal algebraic way, look, you first multiply by 5 and then you end up dividing by 6.
Yeah.
With the Egyptian way, you did it the reverse. You started by dividing by 6 and then you multiplied by 5. You're doing the exact same thing.
Yes, that's right. You're dividing by 6. You still are multiplying and dividing. It's just that you're doing it in a different order.
Right. Isn't
That's
that cool?
right.
That's pretty
Very
cool. I
nice.
thought. Yeah. All right, I'll stop
Very
sharing.
nice.
I
Now
also
here-
realized, Professor, that they must have had a concept of inverse relationships too. Is that
of,
true?
of what type of relationships?
Inverse relationships, like that division.
Yes.
Multiplication is
multiply.
the inverse of division.
Oh, yeah. Well, they would often write when they divided, they would say, this multiplied by what equals that? Multiply to get this was their way of saying dividing. Like they would say 10 multiplied by, they would often describe a division problem with the word multiplication. Now check this out. Here's what I would want to see. And you might look at this and say, okay, I guess I divide, I multiply. Now, if you wanted to use modern methods, 21 divided by 6 is 3.5. This you could do, but for whatever reason, I have a real soft spot for this problem. So I want to see that you do the division the Egyptian way, and that you do the multiplication the division the Egyptian way. But if you didn't, and you got the right answer, and then on the side, you still get a lot of partial credit. When you keep in mind, your guess is always an integer. So when you do the multiplication, if you put the integer on the right-hand side, it's going to be pretty easy to do the multiplication at the end. We practiced multiplication and division last class over and over. So to apply it to these two questions should be reasonable. Okay, well, this is false position is very slick, very cool. And there's a really good chance on the final exam, I would ask a question that's about this difficulty level. False position using the Egyptian multiplication and division, knowing that it requires guessing, dividing, and multiplying. And I really hope that when you look at this, I hope the example I did before where it was x plus x over 6 equals 15, and the idea that when you guess 2, it gives you 3, which is off by a factor of 5, and then you multiply. It's very similar, except you have to do division to figure out what the multiplying factor is. Okay, so that's, what's that?
Yes, I have a question. So while I was looking, I didn't realize that we always have to use the denominator as the guess. So I did mine with 2. And when I was done, I was asking my group about it. And then I learned that you have to use the denominator for the guess. So my question is, although we get the same answer, would you penalize someone for doing that?
Well, the reason you should use x equals 5 is because it's much easier.
Yes, I realized
the
that.
reason they use that as their guess, because if you guess 2, now you have to divide 21 by 2 2/5.
Yes,
which is its own problem. But the truth is, you could guess anything. But yes, you would be penalized because part of their algorithm is that they knew that the most convenient starting guess would be whatever the denominator is.
Okay, thanks.
But you would still get the right answer at the end.
Is that because you're always going to get 1?
That's right. It's always going to turn, if you put it over itself, it's always going to become 1. So you'll always have an integer to deal with, and you won't have any fractions at that point. Now I'm going to stick around. I have to leave pretty soon. But since class goes till 12:15, I'm going to dismiss everybody now. I will post the homework answers a little bit later today for the older homeworks. and I'll talk if anyone has any questions now. I'll stick around till 12:15. So you could go. I'll see everybody tomorrow. We have a new culture tomorrow. It's China.
Nice. When is the new homework due? The one that you just assigned today?
That one's I'll make due. That one's due 2 days from now. I'll make it due 2 days from now because we don't really need it for tomorrow. You know, it's not like tomorrow's not dependent upon it. So let me, it says due today. That's not right. So let me change that.
And there's just Google Sheets, right? No Delta Math.
That one's just a Google sheet, yeah. And I'm gonna make that due on Wednesday.
Thank you.
Let me take a quick look at what the questions are. I think this homework's only like less than an hour, maybe even less than that. Let's just look at what it is. False position. We did 2 of these already, 25 and 27. So there's only 2 questions here. And then the Egyptian geometry. Only 3. So this homework it's only like a 15-minute homework assignment.
Some of us 45
That gives
minutes,
us-
but we appreciate that.
Yeah, the flexibility is nice. Thank you.
Thank you.
Well, the math majors are going to get an extra question though, based on the question I didn't teach today. But listen, this was a pretty fun day actually, with the different Egyptian false position and the area formulas and the pi and did they invent pi and why does Wikipedia? Why do I get angry when I see Wikipedia?
Right.
If anyone's a Wikipedia editor, oh Kamala, I see your hand up.
If we see a
That
rant on that page, we know it came from you, Professor.
I want to become a Wikipedia editor and fix it, but I never got around to doing that.
Professor, can we interpret from your homework assignment that the advanced fractional division is, we can kind of overlook that as just exploratory?
Yes, because there's a question for the math majors that requires that method for, get this, for a step within, no, not a false position one, but there's I mentioned you could also just do regular division to solve, and there's a division, but it's so hard of a division question that it requires that crazy advanced division.
Gotcha. And also,
So no, I won't.
Okay. Are there 2 separate finals too? Is there a math teacher final versus a math major final? I kind of starting to understand that. Okay.
Yeah, the math majors have different final.
Okay.
Professor?
For the math teachers, I'll make either, if there's easy, medium, hard, I'll pick either an easy or a medium version of whatever topic I'm having you do. And for the math teachers, it'll be medium or hard.
I got you. Thank you.
Professor, I have a question.
Yes.
Over the Delta Math, some of the assignments, because I joined the class late, I'm sure you remember me, but can I still do them and get the credit for them?
Yes, it
Because
might.
it says, some of them says already no credit.
I see. I will change the deadlines so that, and I can after the fact. Does it let you do it? Does it let you do it at least, or it doesn't even let you do it?
I think it does. I haven't tried yet. I'm only doing the ones that it allows me to get the credit for. They're due soon. But the ones that says no credit, I haven't attended yet.
I'm gonna fix all those so that if you do it at all, you'll get the credit for it.
Also, the written homeworks, should I submit them on the Google Classroom?
Yes, submit them on the Google Classroom. So I get a list here of how many people turned it in and all. 16. Ooh, that's not good. Oh.
Okay.
So some people I have to go through these, but
You just want like a PDF file, right?
ideally it's a single PDF file. Yes,
Okay, thank you.
you're welcome.
Professor,
Okay.
do you have a date for the finals? Yeah.
I think it's August 2nd.
August 2nd. Okay, because I need to get a babysitter.
I think it's Tuesday, August 2nd.
Okay.
I thought for a second that it might be August 3rd, like that Tuesday, August 2nd was the last day of class, and then there was a final. But no, I do think it's August 2nd.
Okay.
And that'll be our regular class time, right?
Regular class time. We'll all come in. Okay. Any other? I see Molly I see a hand on for Molly.
Hi, I just, I know that you had posted a different homework now, the multiplication and division one, but on the one that you
The
originally.
easier one.
Yeah, but the first one, like on those division problems, like say like the first division problem, 22 divided by 10, you wrote start with 1/2. Like, did you mean like literally like go 1/2, like we don't multiply by 2? Because I was just kind of lost, like.
Oh, no. I meant when it's
go
time to start. When it's time to do fractions, start with 1/2. Yeah, instead of
I was like,
2/3.
I feel like I'm doing it wrong, like, but it's okay to go up and then go.
Yeah. I should have been more clear about that. I meant when it's time to start looking at fractions, start with 1/2.
Okay. No, as long as that makes sense. Thank you.
You're welcome. Okay, everybody.
Good one.
So sorry, I have to run in a sec because I have another a different kid with an orthodontist appointment. So I have to run, but I will. Oh, and let me stop the recording. I'll post the video for this.